Sudah you tekan? Have you started recording? Okay, yeah, all right. Okay, so today we are going to look at paper 51, June 20. So the first question is looking at trichloromethane with propanone, and then they have interaction between each other, and the interaction is permanent dipole interactions. Okay, so that is an attractive force. When trichloromethane is mixed, a strong electrostatic attraction forms between the two different molecules. There is the electrostatic attraction is due to the lone pair on oxygen and the hydrogen that is attached to carbon. A student plans to perform an experiment to investigate the strength of this intermolecular force by finding the temperature change when equal volumes of trichloromethane and propanone are mixed together. State and explain your prediction for the temperature change for this experiment. So it looks like they are forming a bond. Okay, so when a bond is formed, they release energy. So you would expect it to be exothermic. Okay, exothermic will release heat. So what happens to your temperature? Increase or decrease? Temperature will increase. The reason for that, well, my reason is bond or formation of intermolecular forces. Okay, so there is an attraction that is being formed for 1 mark. Next, the student is given only the following equipment and chemicals for the experiment. So you're given a 25 centimeter cube beaker. So imagine a 25 centimeter cube beaker is very small, okay? The one that you usually use is either 100 or 250. Okay. And then you're given thermometers, 2 times 25 centimeter cube measuring cylinders. So measuring cylinders usually to measure out the volume. 50 centimeter cube of trichloromethane, 50 centimeter cube of propanone. Outline the method that the students should use in this one experiment to find the temperature change when trichloromethane is mixed with propanone. Give details of the volumes of liquid used and any readings taken. Okay, so volumes used. You want to mix equal amount of the two reagents. And the total of these two reagents must not be over 25 centimeter cube, otherwise it will overflow. Okay, so we can use 10 centimeter cube. Okay, so we can say that we use equal volume, maybe 10 centimeter cube of trichloromethane, and also 10 centimeter cube of propanone. So that the total is equals to 20 centimeter cube. Okay, even 20 centimeter cube is already banyak, because otherwise when you stir them, it will, there's a high chance or highly likely that they will spill out or splashes out, right? So if you want to use a smaller volume like 5 centimeter cube, that's fine as well, as long as it's equal. Okay. All right, readings taken. So you want to find the temperature change. What do you need if you want to find temperature change, delta T? How do you find delta T? Initial and final, or the highest temperature. Okay, so we measure initial temperature and final temperature. Okay, but usually during this experiment, we take the temperature every, there's an interval of time, okay? We also need to make sure that, okay, so that's in the method use. So method use, first we mix the two liquids or mix the two reagents. Mix the two reagents. And stir, okay? Mix and stir is the same thing already, right? And then we want to record temperature every, what's the interval that you would like to use? Every 30 seconds or every minute? Okay, every 60 seconds is fine. 30 seconds is also fine, just not every 10 seconds. Okay, that's too much. So every 1 minute is also fine until the maximum temperature reach. Okay, how do you know it's the maximum temperature? When it starts to fall down, when it starts to decrease again, okay? When it starts to decrease again. You okay, Nina? Okay. Next question. I don't have the question, but I'll just let you copy this down first, and when you're done writing, we'll move on to the next question. Okay, Alicia, okay? Okay. The apparatus used leads to significant heat loss. Okay, so what apparatus are we using here? Our only concern is in the beaker because that's where we mix the solution, and that's where the reaction happens. When carrying out experiment that involves heat, temperature, what do you usually use in the lab? The polystyrene cup. Okay, so you can use polystyrene cup or styrofoam cup instead of glass beaker. And then they also accept so they want to reduce heat loss. You can use a lid, okay? You can also cover beaker with a lid. And the last one that they accept is you only need one to insulate the glass beaker. So usually you insulate is you wrap around the glass beaker so that the heat loss is minimal. Okay, trichloromethane and propanone are both volatile and flammable. State one relevant precaution that should be taken when carrying out this experiment. So if something is flammable, you do not want to bring it near to an open flame, okay? So we do not perform, don't carry out the experiment near any naked flame. Or if you don't want to use fire, you can use electric heater. Okay. State 1 change, apart from reducing heat loss, that could be made to improve the accuracy of this experiment. There are a few things that you can change. First is in terms of apparatus. Okay, so what apparatus did we use to measure out the volume here? We're usually using measuring cylinder, right? What's a more accurate apparatus to measure out volume? Yeah, we can use a burette. Okay, so use burette, that's only for 1 mark. Use burette instead of measuring cylinder to measure volume, right? Or in terms of percentage error, okay, when we look at percentage error is equals to total error over value used times by 100. Okay, so if you want your percentage error to be low, your value here can be volume, can be mass. In this case, we're talking about volume. Okay, should you use a bigger volume or a small volume for your percentage error to be low? You will use a bigger volume. This is true for volume or solids or other things, okay? So bigger volume, bigger amount of something carried out in an experiment would result in a smaller percentage error, okay? So use larger volume of solutions so that you get lower percentage error. Okay, so this formula is useful, and they always ask you to work out the percentage error for a particular experiment, and it's associated with the apparatus. Okay. Okay. Next is calculation. To find the number of moles, you use mass over MR. I would expect you to have already calculate the number of moles of trichloromethane, which is just 37.50 divided by 119.5, and you should get 0.214. And then for propanone, same thing, mass over MR, it's 0.341. Okay, now, when you want to find the enthalpy change, delta H, which is for the next question, usually the units is in kilojoules per mole, per 1 mole of something, okay? But per 1 mole of what? Because you have trichloromethane and you have propanone. And if I use the number of moles of either one, then I would get a different answer, okay? So you have to choose which one, which number of moles of which reagent would actually matter. And it's usually the one that is in limiting amount, which is the limiting factor. Since they react in a one-to-one, one molecule of trichloromethane would form a bond with one molecule of propanone, so that's 1-to-1. Which one is the limiting factor here? Trichloromethane, usually the one with a smaller amount or the smaller number of moles. So your limiting factor is trichloromethane. Okay. So the statement here said that the energy release, so energy release is exothermic, negative value, okay? So 1.67 kilojoules is released when released per 0.314 mole of trichloromethane. Do you agree? Trichloromethane. Okay, so we read this statement again. In an experiment, the student used 37.5 grams, which is 0.314 moles of trichloromethane and 0.341 moles of propanone, and determines that the energy released is 1.67 kilojoules. Okay, so that means the energy released per 0.314 moles of trichloromethane is 1.67 kilojoules. Delta H is kilojoules per 1 mole. So how much energy is released per 1 mole of trichloromethane? And that answer is how you get your delta H. Don't forget to add in your own sign. Since energy is released, heat is given out, it is negative number, negative value. The answer should be 5.32 kilojoules per mole. You don't need to convert, don't need to divide by 1000 because it's already in kilojoules. If the energy released is in joules, then you have to divide it by 1000. You know how to work this out? You just do the ratio, okay? Okay. Next, if you haven't finished doing that, just write down the numerical answer, negative 5.32 kilojoules per mole, and then you can continue to work it out later at home, okay? It's negative 5.32 kilojoules per mole. Suggest an experiment the student could carry out to test whether the number of moles of trichloromethane affects the temperature change delta T. So at first I thought, okay, if you want to change the number of moles of trichloromethane, I would change the volume of trichloromethane, because changing the volume would also change the number of moles, right? But in the mark scheme, the answer is keep volume of trichloromethane constant. You don't change the volume. But to change the number of moles is by changing the other person, okay, the propanone. So you change volume of propanone instead. And of course, record the temperature. Okay. How does this work? Now, the way I understand it is that they want to keep trichloromethane. They want to keep the volume of the trichloromethane to be the same, constant volume. Okay, so constant volume, imagine I'm not changing anything here, and say I have 10 molecules, 2, 4, 6, 8, 10. 10 molecules of trichloromethane, okay? The other person is your propanone. I change the volume of propanone. Say if I use a smaller volume, there's only 3 molecules. So the reaction, the formation of the force will only be with 3 molecules of trichloromethane. Okay? Now I want to change what is the effect of changing the volume, the number of moles. Now I use a bigger volume of propanone. I'm changing propanone still. Say 6 this time. So how many moles of trichloromethane? Sorry, it shouldn't be T. It should be P. Propanone, propanone. Okay, so I'm changing the volume, also changing the number of moles of propanone. Okay, but this time, how many molecules of T will react my react with my propanone? 6, right? So I'm already changing the number of moles here, okay? So the reason why they want to change the volume of propanone is because they want to keep the volume of trichloromethane constant. Even though the number of moles are constant, but the number of moles that reacted with propanone changes depending on how much propanone I have. If I have 3 propanones, only 3 will form the interaction, okay? If I have 6, only 6, while the other 4 will just swim around there, okay? So this is one way of maintaining the volume of trichloromethane, but changing the number of moles that react with the propanone, right? So that's a little bit confusing because as I understand it, when I see the question, okay, we want different number of moles of trichloromethane, I would obviously change the volume of trichloromethane, okay? So that's a little bit difficult to, it's not something that you would come up in the exam, but with explanation, hopefully you can understand why. Okay, right. Next, we move on to question 2. Okay. Nitrogen dioxide can be prepared by strongly heating lead nitrate. This is a thermal decomposition. So when you heat lead nitrate, you form a solid lead oxide, you form a nitrogen dioxide gas, and you form oxygen gas. So there are 2 types of oxygen here. The nitrogen dioxide can be separated from the oxygen by cooling the gas mixture produced until the NO2 condenses and the oxygen does not. So basically you want to liquefy the gaseous nitrogen dioxide. It will condense into liquid form, okay? So here's the melting and boiling point. What we're interested in is the boiling point because that's the point where your gas would turn into liquid. 294 Kelvin is about 273, yeah? 21 degrees Celsius. And then 90 would be around 273. Negative 183, correct? In degrees Celsius. Okay. Notice the 273. Yeah. So you can see it's not possible to liquefy oxygen in a lab. Okay, say in a school lab, right? It's difficult to get a temperature of negative 183. But for nitrogen dioxide, you see the temperature 21 degrees Celsius. At 21 degrees Celsius, the nitrogen dioxide will turn into a liquid. So it's easy to get 21 degrees Celsius. You just add ice to your tap water. Your tap water is probably around 25 room temperature, assuming that the tap water is the same temperature as your room temperature, it would be 25 degrees Celsius. So the fact that you need to decrease the temperature down a little bit, you can use ice. Whereas negative 183, you cannot achieve that temperature using ice. It's impossible. You would need a more complicated setup, okay? Right, draw a labeled diagram of the laboratory apparatus. So it's mentioned here, lab apparatus, assembled that could be used to prepare liquid nitrogen dioxide from the thermal decomposition of anhydrous lead nitrate. So first I started with the thermal decomposition of lead nitrate. You just need a warming tube, okay? Or you can use a flask, conical flask, as long as the most important thing is that you have a sealed, okay? So you have a cork or you seal the test tube so that your gas cannot escape, okay? The next part is to liquefy your nitrogen dioxide. So usually when we want to condense something, I would use a Liebig condenser, but with a special, mana bro, Liebig condenser. Looks like a hot dog. You all know what a Liebig condenser, right? Is right, okay? So the Liebig condenser is special. Then you just have a something to collect the liquid. Collect liquid NO2, and then this is a Liebig condenser, or just condenser is fine. Okay. Now, what's the special additional modification here is that your Liebig condenser, it is not enough to use tap water. You need the tap water to be cooled down to 21 degrees Celsius. Okay, so you say you will use cold water or ice water at 21 degrees Celsius. If you say tap water, your nitrogen dioxide will not be liquefied. Okay, so you must mention cold or ice at 21 degrees Celsius. Okay, the setup that they have in your mark scheme, I don't like that setup because it's not, they use what you call as a U tube. There's literally a tube that is U in shape. I don't have the mark scheme here. Nada. Okay, never mind. But I'm just going to use this. Tapi you have to emphasize on the temperature. Okay, it's not enough to use tap water. Okay, so how do you get marks? 2 marks for this. Heating a tube containing lead nitrate. Okay, so I've got that. You can also write down Bunsen burner. That's fine. Second mark is for using ice water and a collection vessel. Okay, yeah. So you must have a condenser that is cold at 21 degrees Celsius and also a collector to collect the liquid. And of course, at the end of the collector, it cannot be sealed. Otherwise, how are you going to collect the liquid, right? Some gas will escape, oxygen will escape, but nitrogen dioxide will not escape because this region is cold. The gas will turn into a liquid. So that's where your nitrogen dioxide gas turns into nitrogen dioxide liquid. Okay. Next question, while some of you are still copying that down. At room temperature, nitrogen dioxide exists in equilibrium with dinitrogen tetroxide. So NO2 is brown in color, N2O4 is colorless. And then the equilibrium constant in terms of partial pressure, Kp, is equals to partial pressure of the products over the partial pressure of the reactant raised to the power of their mole ratio, or the stoichiometric number. Okay, state the units. So the top fraction, top number is just kilopascal. The bottom is kilopascal square. So you get 1 over kilopascal. So unit is kPa minus 1. I think all of you should be okay with that already, yeah? Okay, how do I know it's kilopascal? It's mentioned here. The partial pressure is measured in kilopascal. A sample, okay, so a student plans to investigate the variation of Kp with temperature. So we want to see how the Kp changes as you change the temperature. A sample of mixture of nitrogen oxides is introduced into a gas syringe. If you're wondering what the nitrogen oxides are, it's the NO2 and the N2O4. The gas syringe is sealed, so in order to have an equilibrium, you need to have a closed container. It is both airtight and watertight. The volume occupied by the mixture is measured at different temperatures. The Kp value is calculated at each temperature. Name the apparatus you would use to heat the gas syringe at different temperatures between 295 and 370 so that a volume reading of the gas syringe could be easily taken. So what's the easiest way to change the temperature in an experiment? I think you use this mostly in bio, a water bath, okay? So they use the term thermostatically controlled water bath, thermostatically controlled water bath. So it's easier to use a water bath that has a thermostat. What a thermostat is, basically it controls temperature. The physicists would know this, thermostats. Do we have a physicist here? Jadi, thermostat apa? Correct, it controls the temperature. Astaga. Okay. All right, and then you're given the different temperature and the different values of Kp. You are to calculate 1/T to 3 significant figures, and then you log your Kp. Your log is usually log to the base 10. All right, if it doesn't mention, it's log to the base 10 of your Kp. You write it to two decimal places, and then you plot your graph. You should get a graph that looks like that. They're not the best. The points are not close to each other. I was actually contemplating between drawing a curve or a straight line. It's stuck. Oh, yo, what happened? Okay, so then I draw a straight line and I can see that they are all okay-ish. They're not on the line, but they are almost about, the same distance away from the line. So your line of best fit does not necessarily mean all your points have to sit on the line. This is an example of a line of best fit where none of the points sit on the line. Okay? So I think the next question wants you to state and explain what your graph shows about the accuracy of the experimental results. Accuracy, are they all on the line? No. So they're quite spread out, okay? So the accuracy is not that great, but of course you don't use that word. We will say it is not accurate. Not accurate as the points are, instead of using spread out, we use the word scattered around the line of best fit. It does not sit on the line of best fit. So that's what scattered means. Spread out. Suggest what the student could do to improve the accuracy. How do you improve accuracy? In general, repeat. Okay, repeat could improve the accuracy, and then after you repeat, you take the average. Okay, so repeat, experiment, and take average. Oh, I missed part 2. Suggest a reason for your answer. One possible reason is the temperature of each experiment is difficult to record accurately. That's the only issue, I think, for you because, yeah, because it involves temperature, okay? And heat loss is not uh, an answer because heat loss is consistent for all the experiments. So there will be heat loss throughout the experiment. So you would expect it to give a constant result still. Next is to find the gradient. I haven't calculated my gradient yet. Have you calculated your gradient? What sort of numbers are you getting? Okay, let's see. Mine is what's your answer? 2482. I got 2705. Any other answer? Should be around 2000. 26, okay. 2600. To three significant figures, so mine should be 2710. 2710 Kelvin. What about the others? What sort of number are you getting? Sorry? 285040. Jadi kalau very different, better double check. Jadi berapa your number? 29. Okay, that's fine. 29 is fine. Any other number that looks odd? Danish? 26? Okay, there's some still calculating their gradient. Okay, so mine is 2710 as long as it's around 2000. Okay, use the gradient to determine the calculate a value for delta H. So if you look at this expression, I will rearrange log Kp, not rearrange, sorry, I will rewrite it, delta H over 2.303 RT. And if you look at your graph, we plot log Kp against 1 over T. So that means this is your y-axis and 1 over T is your x-axis. So this whole thing is your gradient. Yeah? So gradient M is equals to negative delta H over 2.303 R. And you just have to solve this. In my case, my gradient M is 2710. M is gradient, just like your y mx plus, y equals to mx plus t. Y is equals to mx plus c. And then you just have to solve R is 8.31. Okay, R is given to you. 2710 times 2.303 times 8.31 negative. Calculate a value for delta H, okay? It doesn't say to how many significant figures. We will take 3 significant figures. 51900. 51,900, my answer. Is that correct? Can you check your answer? 2710 times 2.303 times 8.31. Yeah, 51,900. Don't forget your negative. Did you guys get a different answer? Berapa? 54,300. It's still 50,000 lah. Okay, so that should be fine. With reference to the results obtained in this experiment, state and explain how Kp varies with temperature. So I would go back to the table. How Kp varies with temperature. So as your temperature increases, yeah, going from 295 to 377, what happens to your Kp? Kp decreases. So there is an inverse relationship. So we say Kp is inversely proportional to temperature. State and explain. Oh, okay. Explanation. Kp is inversely proportional to temperature. Okay, so we have to look at this reaction again. N2, NO2, N2O4, and the delta H is negative. Okay, so as Kp is products over reactants. Agree? As temperature increase, it favors which reaction? Temperature increase, Le Chatelier will try to reduce the temperature by taking in. Okay? So temperature increase, endothermic favored. Yeah? Temperature increase, endothermic is the reverse reaction. So you have more reactants than products. So the bigger your reactants, your Kp will be smaller. T increase, endothermic favor, Kp would decrease. So the explanation to why Kp is inversely proportional to temperature is because delta H is exothermic in the forward direction. That's why as you increase the temperature, the forward is not favored, but the reverse is favored instead. That's why you get an opposite or inversely proportional relationship. Okay, last one. Okay, I'll leave that for you to copy down. With reference to B and the data for Kp in the table in C part 2, suggest how the color of the equilibrium mixture at 370 Kelvin will differ from the color at room temperature. So you need to know the Kp values at these two temperatures. At 370 as well as room temperature is 298 Kelvin. Okay. Right, so at 370 Kelvin, the Kp is around 0.078 approximately. And then at 298 Kelvin, the Kp is about 9. So that's a big number. Okay, so I just used an approximate. 370 would be somewhere here, which is, here. So at 370, the Kp is around 0.07. It should be smaller. Yeah, 0.070. And then 298 is somewhere here, so around 9. Okay, so what happens is that if you look at 370, the Kp is a small number, right? So if you look at the expression of Kp, if it's a small Kp, that means your bottom number is bigger than your upper number, denominator. Bigger, smaller. Do you agree? Small Kp means you have bigger reactants or more reactants than products. So if there are more reactants, you would expect the color to be more brown. Okay, so the answer is difference in color of mixture, dark brown in at 370 Kelvin. Let's have a look at 298. At 298 Kelvin, you have a big Kp, which is around 9. So that means you have bigger product than reactants. Yeah? You have more products than reactants, so it would appear colorless. Right? So that's why it appears dark brown at 370 Kelvin, colorless at room temperature. The explanation is that at 370 Kelvin, there is more reactants than products, aka equilibrium shift to the left. That's why you see more brown. Okay, that is all. You all okay? I think this question is relatively okay. The calculation is also not too extreme. All right? Okay, so that is all for today. Nina, can you please help me stop the recording? And then you all can go. So we managed to finish before 2.